All right, here we are, 6.3 Accumulation Functions lesson. Our objective is to solve some contextual problems involving some integral accumulation functions, which we've seen before, and usually it's within the context of accumulating some sort of area. Now, this particular lesson is going to be heavily free response question focused, so what I would like for you to do is, if you could, navigate to the internet, and if you could call up my website, and we're looking for the 6.3 accumulations page. To get there directly, you could go to calculus, and within calculus, we're in Unit 6, Integration Apps. If you just click on that one, there it is, the accumulation fun. And on this page, you should be able to see that there's a lesson handout there. If you have access to a printer, you could just tap that thing and either download it, print it out, whatever. If you don't have access to a printer, that's okay. Just have, you have all of these questions. And we're going to start with, our warm-up question is this free response question that's right here on the back side. This particular free response question was from the 2018. It was question number 1, as you can see here, is on both the A/B test and the BC test. It was calculator active. Let's take a look at it, shall we? Okay, so people enter a line for an escalator at a rate modeled by the function r given by, and you can see that we've got some sort of piecewise function here, where r of t is measured in people per second, t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. There are 20 people in line at time t equals 0. All right, that was pretty strange. This 0.7 person per second. I don't know if you've ever ridden an escalator and at the end of it, maybe were really, really afraid that you'd get, like your shoelaces would get stuck in and it would suck you in. I think, 0.3 person usually, I guess on average, gets sucked under that escalator and you see them no more. All right, let's take a look at the different parts of each of this free response question. And then we'll examine each part in detail with the calculator. Part A, how many people enter the line for the escalator during the time interval between 0 and 300? During the time interval from 0 to 300, there are always people in line for the escalator. How many people are in line at time t equals 300? And part C, for t greater than 300, what is the first time that there are no people in line for the escalator? And then finally, boom, part D, for t between 0 and 300, at what time t is the number of people in line a minimum? To the nearest whole number, find the number of people in line at this time and justify your answer. Whew, all right, this is how we started the 2018 test on the free response question. Escalators, 0.7 person per second, and a piecewise function. You can bet that it probably scared some people off. Okay, so what I have done here, again, this is right on the back of that worksheet if you did print that thing out, or if you didn't, you can just follow along with me, but make sure you are actually working through this. Okay, so I have went ahead and I copied off the actual equation here and titled this warm-up. Whoop. So we have this piecewise function, and the first part is asking us, let me actually make this a little bit larger. There we go. How many people enter the line for the escalator during the time interval from 0 to 300? And I'm going to move some of this stuff down. Have a little bit more room to work. Okay, so this is what I want, how I want to conceptualize this. So I have this rate, and this rate here, r of t, I do believe that it's measured in people per second. That should have been said. Is r of t is measured in people per second. That's correct. Okay, so this is in people per second. All right, and I need to get rid of the second in order to actually get just people. And the way that I'll do that is I'll take the integral of this with respect to time, and then time, of course, is measured in seconds, and now our seconds will cancel and it'll just give us people. So what we want to do is integrate this r of t dt over the interval from 0 to 300, have that written down. This is a calculator active question, but you definitely want to have that thing written down on your paper, on your actual test booklet, because it's worth a point. That was actually worth the very first point for this question, +1. Okay, and so now we're going to switch over to a calculator app. Perhaps you downloaded, which I don't seem to have here, so let me kick open the apps. And here it is. So if you downloaded the TI Inspire app, this is what it looks like whenever you first call it up and you want to choose a new calculator app. All right, so this is a calculator. Just like your calculator screen, you can see the keyboard and all the different things that you can possibly do with it. And now we want to, I do believe it's on add a graph screen to this. And then this is just like your y equals on your TI-83 calculator, 84 calculator. And now we can type in our function. So our function was, and it's just the top part. So the bottom part of that piecewise function is just 0. We don't have to type that part in there. So we're just going to type in the top part, which was 44. Open the parentheses. Then we have some sort of fraction. We got a fraction button here. And you can see the cursor's already in the top part of the fraction. It says t. We'll just go ahead and use x. And this is interactive enough that you can either use, your finger to tap on where you want things to go, or you can use the little arrow keys that are here. 100 on the bottom. And then we need to come out of it. You see the x squared button right beside it is x to the some kind of power. If I tap that one, I can put it's the third power. And then we need another set of parentheses here. And inside we have 1 minus another fraction, the variable on top, and then 300 on the bottom this time. All this raised to the 7th power. Okay, 7. Bam. All right, so we have our equation in. I just hit enter. Now, one of the things that I want to do on this graph screen here, because I'll probably have to come back to it, is over here by the little toolbar, it says 1.2 has a little wrench, has a little gear there. I'm going to click that little gear. And under display digits, I've actually made this default so that I don't have to do this again. Under float, I want to actually choose float, so it's going to give me all the decimals that the calculator has in its memory, instead of just truncating it and giving me just, say, like a whole number or 2 decimals or something. Okay, so once I get that, I'm going to hit OK. All right, now that was just so that we could enter our equation in. In order to get back to the calculator screen, over here on the left-hand side, with this little menu, I've got rad, and then there's this little box thing. I'm going to tap that little box thing, and then here I can switch between windows. Here's my graph screen window, and here's my calculator screen window. I'm just going to tap that one, maybe. All right. Tap on the screen, and then whenever I tap on the screen, it pulls up the little calculator. So then I can, down here in the lower left-hand corner, you can see the button for a indefinite integral. If you hold it, you'll see an indefinite integral as well. But we just want, of course, the definite integral. We wanted it from 0 to 300. Inside here, we want to put the name of the function, which for us was f sub 1. To easily get that, down here at the bottom row, it says VAR. So if I hold VAR, you can see some different options. Or if I just tap it, it pulls up the available variables. Ooh, that was tough to say. And you just tap on that f sub 1. In the parentheses, it's looking for an x. And then at the end there, I definitely want to put with respect to x. Now watch what happens when I just hit enter. Oh, well, this one was perfectly 270. Well, so this, since it has a computer algebra system, if it is some sort of funky irrational number, it would give you the exact number for that. And sometimes what you have to do is hold this in and then actually choose the approximately equal button. Come on. And choose that one. And notice the difference between these two. The top one says 270, the bottom one says 270 with a decimal, indicating, at least on this program, that it's the approximate answer. So I'm going to write this thing down. We have 270 people. 270 people enter the line, right? Because that's what this equation was here. This was the rate at which people enter the line. Okay, anyway, 270 people entered the line on, let's say, 0 less than or equal to t, which is less than or equal to 300. I don't think on is the correct preposition, but I'm just going to go with it. So we got 270. So that 270 people, that was the other point for this particular part of the free response question. Okay. All right. Wow, that took a long time. That was pretty much our whole 15 minutes there, probably. Okay, so let's look at part B here and move some of this other stuff down. Okay, during the time interval from 0 to 300, there are always people in line for the escalator. How many people are in line at time t equals 300? Okay, so here is where I'll need to take into account both the incoming rate. So let me write something down here. I've got people coming in. I also have people exiting the line, so minus the people that are coming out. But there was one other piece of information that I don't think that I wrote down. Let's make sure that we go back here, and I'll highlight it. There were 20 people in line at the very, very beginning. This is the initial amount. So we have some sort of initial. Plus the incoming rate, and then minus the outgoing rate. So this is kind of a little recipe for how we're going to set up this particular problem. And then I'm also going to say at t equals 0, we had 20 people in line, just as a reminder. Okay, so this is going to be set up very, very similar to, let's say, one of those velocity kind of questions where we have the initial condition, and our initial condition was 20 people in line, and then plus some sort of change, and that change is going to be the accumulated change, which is the definite integral of the rate of change over our interval from 0 to 300. And inside here, I want to do this part here where I have the rates in minus the out rate. Well, it gave us our in rate as r of t. I'm not going to write down that whole entire function. I'm just going to write down r of t. And then our out rate was, it was that really strange number, which again I'll highlight here, that they exit the line at a constant rate of 0.7 person per second. So it is not 0.7 t, it's just 0.7 dt. All right, so this part of the integral right here, this is the change. And the 20 that's over there on the outside, of course, that is, man, it's taking me like my whole entire free response time just to color that in. So here's the change. And that right there is the initial, of course. And if I go back up here to part A, what I did in this integral is roughly the same thing that I'm doing right now. It's this integral that's right here, right? It's just that I didn't have to take into account the outgoing rate. All right, so now it is pretty much a calculator problem. And let's go ahead and switch back to our calculator app. Okay, so I am going to put in 20 for our initial condition, plus we want that definite integral, also from 0 to 300. And inside here, we want that same f sub 1. I pull up my variable menu, hit f sub 1, put x, but then you need to space out of it and then put minus 0.7. And the last thing, of course, is with respect to x. All right, so let's see what it does this time whenever I hit enter. Oh, exactly 80 people. Wow, okay. So this is equal to, try that again. I'll not abbreviate it. People in line at t equals 300. This is in seconds, isn't it? I think so. All right, and so as far as point breakdown goes on this one, as you could probably imagine, the 80 people, that was worth 1. One particular point, your integral, no, it wasn't even the integral in this case. It was the fact that you considered the outgoing rate was worth 0.1. So if you had that 0.7 in there someplace that you were subtracting it out, you got that extra point, that last point for this one. Okay, so we're finished with this piece, and let's look at C here. For time t greater than 0, what is the first time that there are no people in line for the escalator? Well, let's go back to our equation that we copied up here, and remember that for this equation, anything greater than 300, nobody is entering the line anymore. Okay, so we don't have to now take into account the r of t. It's just we have, from this previous part, from part B, we had 80 people in line. We just want to see how long is it going to take for those 80 people to get out of the line, to exit. Well, how quickly do they exit the line? That's that 0.7 person per second. So we're going to take our 80 people from the previous part, divide it by 0.7, and let's see how many people that we've got here. 80 divided by 0.7. See, I got a decimal number here, so I'm going to say that we've got 100. This is amount of time, so we definitely want to use our 3 decimal places there, which is 114, 280, and then round that to 6. It's about 114.286 seconds. However, this is not our final answer, because this is 114-ish seconds after the 300 seconds that have already taken place. So let's go ahead and add our 300 to get, that would be 414.286 seconds. And maybe I write that as a sort of sentence. So in 414.28 seconds, there will be no one in line for the escalator. AP, College Board, you guys are strange. Whole escalator question, what the heck? All right, so let's look at the final part here. Nice fresh page, make this larger. Between 0 and 300, at what time is the number of people in line a minimum? I'm going to pause right there. Minimum. So when they say that word minimum, we're assuming that they mean absolute minimum. If they wanted a relative, then of course they would use that word relative or local. This means that we have one and only one test available to us, which is the closed interval test. Okay, to the nearest whole number, find the number of people in line at this time and justify your answer. The justification for our answer is pretty much going to be what I just pointed out here, which is that closed interval test. Now, in order to start the closed interval test, you need an equation that you can maximize, or no, in this case, minimize, right? So we're going to go back to the previous part of this, and our equation is basically the same kind of thing that we set up here on part B. So from we have some sort of initial amount. We have the definite integral from 0 to, instead of making it 300 there, I'm going to make that a particular value, like a variable value, either a x or a t, but then I have to switch the things up that are right in here. So I'm going to set up that equation first that I have. I'm going to say e of t is equal to the number of people in line for the escalator time t. Okay, so E of t should be equal to some sort of initial condition, which was our 20 people, plus our change. And we're going from 0, that was the initial time, to t. And since I used a t up here, this is the variable for the particular equation, I need to make sure that I don't use t inside here. So this is going to be r of x minus 0.7. That's our in rate. This is our out rate with respect to x. Okay, so now I have an equation. And now in order to find where our minimum is, I'm looking in two different places. And those two places include either, endpoints or critical numbers. Endpoints are obvious, we got 0 and 300, but our critical numbers are going to come from taking the derivative of this thing. So I'm going to take the derivative of e of t, and this should be equal to, well, the derivative of 20 is 0, and when I'm taking the derivative of a definite integral, the thing that happens, since these things are inverses, is I take a change of variables, put it up in here, and we get r of t minus 0.7. Okay, in order to find those critical values, we're going to set that thing equal to 0. So 0 is equal to r of t minus 0.7. And here was worth a point. Did I tell you what the points were for this one? I think on part C it was just a single point. Plus 1. Let me check just to be sure. Yeah, it was just 1 point for the answer. Okay. Now, on this one, we just got our first point. And our first point was considering this rate equation set equal to 0. That 0 is equal to r of t minus 0.7. And I'm going to solve this thing on the calculator. So flip over to the calculator. We need to go back to the graph screen here. So I'm going to hit this little Windows selector button and then go down to the graph screen. Okay, and then right beside the little plus sign, I do believe that we can just, you see there's a little plus sign to add in an extra equation, or right beside it there's this little hamburger menu. If I click that, here's my f sub 1. So I'm going to tap at the end of it, pull out the calculator, and then subtract my 0.7 from that, hit enter. Okay, so now here's my new equation. I may have to zoom a little bit so I can see where this thing is going to hit the x-axis. And it looks like it hits in two different places. So the cool thing about this, of course, is that it's interactive enough that I can kind of scroll and then pinch and zoom and stuff. Okay, so in order to find the actual 0 there, in the case where we had our calculators at school, of course, we would do second trace, go to the calculate menu, and then find a 0. Here we have under the tool menu, we have one of the items is analyze graph. So we're going to choose analyze graph, and then there's where our 0 is. And then we have down here at the bottom, it says lower bound. So we're just going to move our vertical line here to the lower side of this, and it looks like this should be okay someplace in here. And then it automatically, whenever I stop, puts another one in here, and then I can zoom it to the left or to the right. Okay, and it's already kind of found one there. And now, just like with let's say our calculator at school, I'd want to take that number and I want to store it because I'm going to have to use that within the problem. So if I tap on this, I may have to tap a couple of times. I can delete, store, or pin. We want to store this, and then it's going to prompt me, what do I want to store it as? So down here at the bottom, you have x. We don't want to store it as x, but right next to it, we have an a. So we're going to store it as a, and then hit enter. Okay, so that is now stored in as a. And I definitely want to write that number down. This is one of my first critical values, but you can see that I've got another one over here someplace. So let's see if we can find the next one. Hit the wrench, and it's already on Analyze Graph, so we want to hit 0. So let's move this over here this time. Over here, there's the other 0. Let's store that guy as well. So tap one more time, store this thing. And if of course, don't want to store it as A again. So if I hold in A, then I can choose B, and then it's stored as B. So again, I want both of those things written down as my critical numbers. So my critical numbers include T is equal to, I've got 33.013, and I stored that as A. And then I had this 166.575, and then I stored that thing as B. Okay, so here was our next point for this particular problem, plus 1 for the 33.13, and you'll see why in a little bit. Let me go back to the little calculator screen and maybe make sense of it. So we know that we are going to have ourselves a minimum when your derivative changes from negative to positive. And that's what happens right here at this point, but it doesn't happen at the 166. This one's a relative maximum because the derivative, hard to kind of see there because of how small that graph is, but it changes from positive to negative there, indicating that it's a maximum. Okay. So now for the rest of this particular problem, we just set ourselves up a table of values, and it looks like this. So T, and in our table of values, this will be E of T over here, we want to put in our endpoints, so 0, and then our critical numbers, and I'm just going to write this as an A and a B because I've already indicated that I stored them as that, so I don't have to write those decimals down again. And then finally, our 300. Well, we already know the answer for the first one and the last one because we started with 20 people. Another part of the question, we had to figure out how many people were in line at 300 minutes. I think it was 80, wasn't it? It was 80 people. Yep. And now we just have to figure out A and B. So to figure out A and B, I'm going to go back to the calculator. I'm going to plug these numbers into this equation here, right? Instead of the little t there, we'll have the a that we've stored in, and we'll separately have the b that we stored in. So we need to go back to the window picker, go up to the calculator screen, and tap the calculator screen so the keyboard comes up. Start with our 20. Actually, you know what? I'm going to delete this out because I already have this equation in here. If I tap on this, I can copy it and then come down here and paste it, and then go up here to our 300. Delete this thing out. Whoa, hey, don't delete the whole entire thing. Oh, I got a problem here. My f sub 1 is different now. My f sub 1, so my f sub 1 already has this 0.7 in it. So I'm going to take that part out. All right, tap back up here, and I want to just go to A, and then hit enter, and we get 3.803. Where did the other 0.2-ish part of the person go? Of course, got swept underneath. Their shoelaces were untied. Tie your shoes before you go on an escalator. Jeez. All right, and then we need to do the same thing for B here. Of course, this one should be way bigger because it was a relative maximum. All right, so go over here to the A, delete it out, and then if I hold in the A, I should be able to choose the B. There we go. Or if I just tap the variable button, then it would have called up as well, like this. So I have now access to all the variables that we've stored for this particular problem, and then hit enter, and then we've got 158.070. And then we have an obvious winner. We were looking for the minimum, and the minimum happens here at time A, which was 33.13 seconds. Okay, so I just want to write one little conclusion sentence here, because it does say to the nearest whole number how many people, and then, so we're going to round that, I guess, to 4 people there. So, and what time did this happen, right? So the minimum number of people in line is approximately 4 people at time t equals 33.013 seconds. As far as point breakdown goes for that, we had 2 points already given to us, and the other 2 were our, I want to say it's the answer and the justification. So +1 for answer. And then the justification is pretty much everything that is here on the page. It's the closed interval test. All right, so that concludes this opening problem involving the escalator, the famous escalator problem. Like I said, tie your shoes, please, please, please. We don't want to end up like this person. So our objective here is exactly what we were just doing in this previous problem, being able to solve some contextual problems involving integral accumulation functions. Okay, so what I would like for you to do is take a look at the first question that is on the other side of your little worksheet. So if I scroll back over here to my worksheet, back up here. So this time for this particular question, you have a graph. You're given an equation here, and it's an accumulation function. Go ahead and give yourself about 15 minutes, work through that thing, and you've got 2 options. You can either look through the answers for the PowerPoint and check to see if you got it right, or you can watch a follow-up video to this one where I'll take you through it step by step. Boop.